Привет.
Hi everyone, I hope you can hear me, you can see me as usual. If any complaints, please write in the chat or speak out loudly. I will try to fix things. And so we will wait for a couple more minutes for your colleagues to join, and then we will start our next lecture on how can we apply convolutional neural networks for time series and for sequential data in general. Our focus here in this lecture would be more on NLP applications, as we often do, but this tool is also very powerful in other settings because it's kind of has natural processing of the whole series and does not focus on any part of it. Also, convolutional neural networks in general are better than RNNs for many problems, and it's definitely worth a try when you're trying to solve a new problem that's connected with processing of sequential data. And in some problems, and it was in my experience, that CNNs were better than transformers, and I think you should pay more attention to this approach if we are talking about something like not very large data settings, something different from what we have typically in NLP when we learned to train very large model in kind of unsupervised regime, but it's not always the case. Sometimes we have supervised problems, sometimes we don't have large data sets, or they kind of not very expressive. And in this case, CNNs can be quite handy. And so I encourage you to try them and to learn more about them. Especially, I hope that most of you know something about CNNs from image processing. And okay, let's try to have a small poll before the start of the lecture today. And so let's have two questions. The first one would be like, do you know CNNs for image processing? I will prepare questions in 1 minute and give you access to them. Yes, now. After that, we'll continue the lecture. Maybe Rodrigo give you some clues on how to do those kind of things. But I think it would be useful to do something like this now and repeat it to get a systematic view on what can be or can be done.
So to add to that, we had a small discussion on quasi-recurrent neural networks, and so yes, that was basically what we discussed on using CNNs for time series, but otherwise we have primarily discussed RNNs. So a lot of new things to learn today.
Okay, so let's see what you can answer, because I have a specific file devoted to this topic. So I suppose it will be easier for you than just. Okay. Then just write something in chat, because I suppose that some of you are quite confusing about this thing. Okay, so it's very good that all of you know something about CNNs, at least that part of you that have been voting. Now, also about sequential for sequential data, we see that kind of even score, but more votes on the side of you know something. And I hope that you will know more about this lecture and maybe a couple more lectures. So I can show you results if you want to look at them. So you can identify in what group you are, and we can continue the lecture with more detailed introduction to this kind of models. And as usually, I want to start from motivation, why we even want to do this kind of things. Maybe the strong motivation comes from a different area when we are looking at success of convolutional neural networks for image processing. In this case, we can say that right now, convolutional neural networks are the king in this area. Sometimes there are some papers when, especially recently, that there has been some success with usage of transformers for similar problems like ImageNet, but I suppose it's not like a mainstream direction, and it's not like everyone is trying to use transformers to improve their image recognition models, especially if they don't have large amounts of data. Instead, convolutional neural networks are the current state of the art in this area. It is because of the quality and the recent success in deep learning in general, and for image processing, specific area like image processing. I suppose it's mainly due to right usage of convolutional neural networks. The common example is this ImageNet, when you have like 3.5% of errors for top 5 guesses for ImageNet problem, and it is better than humans, and it's better than pre-convolutional neural networks. I suppose that it was like error rate like 25% for pre-convolutional methods. So, okay. As you can see, there is one motivation. Another motivation, actually, I showed this plots from different perspectives. I think like 3 or 4 lectures ago. It's about how different models are ranked when we try to translate things from language to another. And as you can see, we have this below score, the score that we want to maximize here. And there are 3 competitors. Recurrent neural networks, about what we talked during the first 2 or 3 lectures in the course. Transformer architecture that we also talked and is the current state of the art now. And so we have 2 models in between for the left plot, and 1 model in between for the right plot, and these models are convolutional neural networks. So it was kind of very good when this paper appeared, and like it was worth to compare transformers to them because they were even better than RNNs. So at least we can say that RNNs are not as good as CNNs. So we spent a lot of time trying to understand what's going on in recurrent neural networks world. So we should devote some time to CNNs, and so this is a second part of our motivation. They're quite good at some problems, maybe not as good as transformers, but very good. And when you compare CNNs to the previous models in this area, and you can see that there can be like a lot of them, a lot of variations of CNNs, and a lot of approaches published before CNNs. Like this is from paper that was published in 2014. And in this case, okay, they compare it to RNNs, to, okay, even to SVM here. For some problem, they compare CNNs for 7 diverse datasets from NLP. And what we see is that actually very simple CNN models with kind of 1 or 2 layers can be as powerful as many other models that were that they tried to improve for many years. And we will discuss, is this comparison fair, closer to the end of the lecture, but it's kind of a good motivation to study CNNs. Okay, it was very good motivation in 2014. Now we have kind of different era, but still I suppose that these results are important to understand why CNNs should be used and should be compared as a baseline. When you compare this approach to RNN, you definitely can say something about why we should use something different from like very general linguistic or common sense point of view. As we already discussed, RNNs are trying to put all information into this hidden state, and so we can miss something that is in the very beginning. It can be quite a pity because we can lose significant amount of information, especially if you're trying to make a single decision on the basis of the whole sequence. So it's kind of bottleneck, and also it's like experimental fact that if we focus on that we try to use RNNs, we mostly focus on the last tokens because, okay, not much information is going through all this forget and update layers. Also, another reason that kind of connected to the first one is that right now we can see that RNNs are mostly used in this straightforward way when we pass information from left to right. And so in this way, we kind of can't incorporate all the information we have. Okay, we, and not only we, but scientists from all over the world tried to kind of overcome this difficulty with, for example, bidirectional RNNs or multi-layer RNNs. And typically, if we do it right, multi-layer RNNs and bidirectional RNNs are better, especially in the problems when it's kind of beneficial to use information from the whole sequence and to have a run not only from the left to the right, but also from the right to the left. And in this case, maybe there can be less like kludge solution to this problem when we are trying to incorporate this information directly about the whole sequence, about this part and this part and this part. We know some solution to this problem, and transformers are really trying to match everything to everything. And it kind of works, and we have very strong results from them. But there is still a problem that's common for both RNNs and for transformers too. They can be quite long, take quite long time to train and to make inference. In particular, when we are talking about transformers, they have like S squared complexity when we're doing all the stuff with attention, because if, okay, S is our sequence length, and it can be prohibitive if we have very long text. And I think maybe CNNs can be a better solution to this, both in terms of quality, because we are paying attention to only to our part of the whole sequence each time, but also in terms of computational time. And I think that CNNs can be better at training speed than both RNNs. That actually takes very long to converge because of this passing of the gradients to the past in a very slow way. So it kind of requires a lot of epochs to adjust passing the memory from very, very, very distant past. And instead we want to, okay, so we see that RNNs are not good at this, transformers are not good for computational time. So what else can be offered to improve this kind of results? The idea is the following. We will compute embeddings for all subsequences of a certain length. So a kind of, if we have this guy here, a sentence, then we will try to generate some features based on, for example, triplets, based on each 3 consecutive words here. And in a way, we impose some constraint of the range of the dependence. Okay, we will see how to overcome them, but it can be a good way too, because as you know, for many sequences, we are very interested in trying to compress information from like part of the sequence, and it can be very beneficial in many, many scenarios. From very like straightforward linguistic, we can say that it's kind of very reasonable approach, and we have some language laws about how the sequence behave, but from like a common sense is kind of come naturally. We want to combine like not very distant information, and then also we can try to build on this formation like new layer, and finally we'll come to a neural network that's like kind of similar to what we have for images, when we like start with a reception field of very small size. So it's kind of when we are looking at the first layers of convolutional neural networks, we try to aggregate information from these small parts of the image, but later when we pass through like many convolutional layers, in the end we have receptive fields that is very close to the whole sequence, as a whole image. And so in this way, we can say that we try to aggregate the information from the parts, and it makes sense because we believe that if we have information from like a small part of a sequence, then it's okay to, it's a good point to start, and it can be meaningful, and also it will help us to solve some problems. But also if we will be able to stack more layers and to increase our reception field, kind of range of the data we see at each neuron of subsequent layers, then we will be able to use this convolutional neural networks machinery, and the motivation will be similar to what we have when we use CNNs for computation. Okay, this is the end for the motivation part, and I hope it's clear, but try to think about it one more time, and if you have questions, please write them down. If no, please write a plus sign in the chat. So I will be really happy about the feedback. I think that transformers can be quite computationally demanding approach. Yes, but it's kind of not a vanilla transformers, and so maybe we can try to like compare vanilla approaches from the very beginning, and okay, it would be the next step to compare not vanilla but advanced methods. And I think it's quite maybe it's a different ways to think about the same thing, about that we try to kind of divide information we have to parts, to batches, and proceed them in a separate way. And I think that another motivation is that like we try to adopt the successful computer vision approaches, but I understand that all of this is kind of like not something that you should take at the first look, and it's more like speculative arguments. And okay, I think it's in the end we will just select a model that is the best for a particular problem, and later we will see, okay, at least not at this lecture I suppose, but I hope maybe later, why convolutional neural networks make sense, not only like from the general point of view and the general motivation, but also maybe for some problems we will consider some examples of how they work or don't work. Okay, thank you, Mark, for the question. And so let's introduce the architecture. I think that in next slides you would have some kind of deja vu, as if you are familiar with convolutional neural networks, because the set of operations is kind of similar for what we had for convolutional neural networks, for sequences, and for usual convolutional neural networks. So that's good from one point, because it will be easier to understand. So for what we are doing when we are trying to do convolutions for images, we have some input to a convolutional layer, and we want some output. And this output is produced using like a convolution with a kernel. So the kernel is the same for all convolutions in our parts of input. And what we're doing, we have multiply these two matrices and sum the results. It's kind of 1 by 1, 0 by 2, 0 by 3, and 1 by 4. We sum this in, and we have 5. Then we go to the next part of this image. It's like 0, 1, 1, 1, and it's kind of 9. It's 9 here. Then we go on with 4. Then we go to the next row. In this case, you consider these two guys, and it's like 5, and so on and on and on. And in the end, we have this output of the layer. It's beneficial in terms of number of parameters, in terms of computational speed, because we can use GPU to very fast calculation of the result in convolution. Also, we can easily backpropagate in the reverse direction when we want to update the parameters of this guy. And when we stack all these convolutional layers, we will have very good models typically, and most modern models like ResNet, VG, and even better or smaller or in any way good models are kind of good when we are talking about this kind of thing. Okay, I will have a simple sheet here, and I hope that we will not disturb you too much. It's not very convenient for me to have. No, it's not okay. And so, okay, everyone knows this convolution, and we want to do it for images. Okay, we apply the same formula. We have this input sequence. We have kernel of size m, 2m's plus 1, and we kind of can do it in one-dimensional and in more-dimensional. Suppose that we have embeddings of words here. So we have this word now, embedding for it has g equals 3, and it's kind of 0.1 minus 0.2. 0.4. And for other words, we also have embeddings that are provided for us, for example, by word2vec. So we have numbers from the very beginning. In this approach, it's like not necessary, but it's kind of a good idea to start. Then we have a kernel. The kernel in this example is something of size 3. It means that we proceed the 3 rows here. And we say that we multiply each guy of we have in these embeddings and each guy in this kernel. So we multiply 0.1 by 3, minus 0.2 by 2, and 0.4 by minus 1. And if we sum all these numbers in this part, we have kind of this guy, this number. Then we continue with the next, with embeddings for the next 3 tokens. And again, we apply this filter and get 0.3. And again, and again. And in the end, we have like for each triplet and a feature. And so after that, we kind of applied one-dimensional convolutional. One-dimensional because we go only in one direction. For this kernel, we don't go in this direction because like we don't care about this. Okay, maybe it's an interesting question to try to do this kind of two-dimensional convolutions if we have very large embeddings and we can train them, and maybe someone did it. But okay, the mainstream approach is the 1D convolutional when we use this kernel for one-dimensional processing of consecutive triplets, or not triplets, maybe big grams or many grams for each part of a sequence. And so this is a very basic thing, and we actually need some update for it for the battery life. And what we also can do. For example, a good idea is to have padding. In this case, we have two mask tokens in the end and in the beginning. And for these two tokens, we have 0 embeddings, or whatever embeddings we learn from our data. Then we apply the kernel in the same way. And so we have two additional guys here, okay. And the size is similar for input and output of this layer. So we have the similar lengths. And it can be beneficial and can be not avoid some confusion when you have many layers and so on. But okay, I think that you know all of this from computation. Here we also have bindings. And finally, we want to do some kind of predictions. But when we have at this stage of application of one-dimensional convolutional neural networks, then we still have many numbers, a vector. And the size of the vector actually depends on how long the initial sequence is. So if the initial sequence is of length, 7, then output is also of size 7. And if 9, then 9, and so on. So we have many features. And what's more important, the number of features is different for each sequence. But we should somehow want to aggregate all those guys to a single number or to an embedding of the fixed size for a sentence. And so what we try to do, what we can do another thing from convolutional neural networks. We apply pooling. So we look at, first example, max pooling. So we kind of look at all those numbers and select the maximum value. So it's 0.7 in this particular case, and we have the single feature. And it's kind of good for obvious reasons. Now we can, for example, say that if this guy is bigger than 3, then it is positive. If it's smaller than 0.3, then it's negative, and so on. So it's kind of fixed dimension representation of the data. This is what we always aim at when we are working with sequences, because we are often confused about the different lengths of the sequences. For sure, we can try to try a different approach and say that instead of max pooling, we want min pooling. And in this case, we just have mean value of all those guys. And as for max pooling, we can propagate the derivatives and learn this filter to improve our beautiful model, or even can try to improve the embedding in the same way, because we can do it. We can propagate the gradients, update it, and apply all the different machinery. But I suppose that one feature is not enough, and we can try to do many filters. We can do 2 of them. And in this case, maybe filter is not maybe the best word here. We can say something about channels, and I think it would be a better representation of what we are talking about. But in the end, we kind of have dimension for this as the output of the layer, or for min pooling for this layer, similar to the number of channels for our filters of this particular size. And so we can try to have many channels, many kernels. we can increase dimension as long as we are happy about the result, and as long as we observe some kind of increase in the quality of the models. So again, this idea is not new, I suppose, for you, and this is what we already been doing a lot when we were talking about convolutional neural networks. And to sum up this part, you can try to imagine a code that works something like this in PyTorch. So we initialize batch size, initialize word embedding size, sequence lengths, and so on. And what we can do, we like say that we have this one-dimensional convolution. We know the input size of this convolution. We know number of channels for it. We know the kernel size. And if you want to produce a hidden state, we use this one-dimensional convolutional layer. And then if we want to apply max pooling, we do something like this, select the right dimension, and put hidden one as an input here. So kind of pretty straightforward, kind of similar to what we expect for two-dimensional convolutions. Also, we say that, okay, that we have similar hyperparameters like sequence length and additional parameter which is similar to all other methods we talked about, in particular about this word embedding size for. Okay, nothing too surprising to the moment. Also, some things from this convolutional neural networks and from general intuition also works here quite well. For example, we can say that we can, okay, let's go step by step here, start with stride. In this case, we kind of not interested, we're interested in this guy, in this guy, in this guy, and we are not interested in this like even triplets, like this guy or this guy, because we see that, okay, we don't lose much information, but because okay, we have very high intersection between this, and in this case, we can say we can have stride 2 and avoid convolution of some layers, and then have not like 6 by 3 matrix. Instead, we can have like 3 by 3 matrix, and it can be good for some applications. It's another hyperparameter to optimize. Also, we can try to do kind of local max pooling for like when we have output of our one-dimensional convolutional layer. We can say that we want max pooling not for all sequence, but we want to do this max pooling partly. For example, we can say that, okay, to produce the first maximum, we take this first 3 guys, and we have this like 0.6, 0.2, and 0.4. Then we go to the next guy here, and again we apply max pooling to it. And this guy, 0.6, 0.5, okay, and so on. So we have it like this, and it can be like good idea, good way to start, and also kind of a way to reduce the number of computations, and in a way to introduce this multi-layer structure, because we now have to proceed this guy, and we again apply one-dimensional convolution, which can be quite. Also, another like not very complex but sometimes working idea is top k max pooling. We can say that we are not interested not only in max value but in top 2 values. So, for example, for max pooling, we have 0.9, 0.5, and 0.1 here. And we can say we also interested in top 2, 0.7, here is 0.2, I suppose, and 0.6. And we can try to do it like this, or we can instead try to like count them as they occur in the data. And in this case, it will be not like this, but more like 0.9, 0.7, 0.2, 0.5, 0.6, and so on, because the 0.6, for example, is before 1, and we like count these poolings not like in sorted order, but in the order of appearance in the data. Okay. Also, on top of that, we have this usual idea to have more layers. Okay, we skip modulation because it's kind of similar to what I already told, I suppose. What I want to add is that we can have multiple convolutional layers. Because if we have output like this, or even before pooling, we can try to apply another convolution. In this case, we kind of increase the reception field. And we see that if you have like these two kernels of size 3 by 3, then for the first layer, we kind of aggregate information from these 3 tokens as the output of this layer. And if we apply the second convolution here, we have bigger reception field. We add these two guys when we're talking about the first element of our convolution. And so if you have more layers like this, then in the end, we kind of observe the whole sequence and can try to match very different tokens if we need them, because sometimes we need like very distant information in the sequence. So this idea are also useful, and okay, I understand, and so on. Let's put more formally what we were doing for this one deconvolutional layer, and I will follow the okay, not notation, but like formulas from this guy, and also from the Stanford NLP course on okay, natural language processing, CS 224. But I thought it would be useful to look from a bit different point of view. But again, a question. Do you understand what is going on? Please write a plus sign if you understand everything before this point, and try to think about some questions about what you want, what you can ask here. Oh, okay. Okay, very good, very good. Actually, yeah, I think it's a good point about what kind of filters we can expect when we're thinking about NLP data. And we can look at it from 2 points of view, actually. The first point of view is that we go to pooling and we can try to catch different things with different points. When we have max pooling, we can say that maybe, okay, let's go to another slide here. Maybe we have some specific feature that is devoted to, like, is this word related to positive or negative reviews? And if the magnitude of this feature is high, it means that it's very highly positive word. And if it's like low, it's kind of related to negative reviews. And if we use max pooling, we kind of extract the maximum value of the most positive word. And in this case, we can say something about the positive attitude of the review in general. From other sense, maybe sometimes you need some kind of average type of average or mean value of this impedance. For example, okay, maybe it can be kind of classification of text to topics. And in this case, we kind of want to have like mean value, just because it could be more interesting thing to look at. In this case, we can try to do mean pooling, have like mean or average relation of this text to a particular topic. Also, moving to the second part of my answer, or the second possible answer to this question, I think we can't do it like this, because we I think even now in 2020, no, not too much about embedding, not too much like what features are related to what, and it's very hard to interpret them like this. So we kind of have very abstract numbers. We can say that, okay, if we like have king and queen and we have equations like this, okay, we have some relations in this embedding space, but generally we don't know too much what component relates to what, and so it's kind of hard to invent some meaningful filters like trying to sharpen the edge. We can only say something about in general sense like min pooling, max pooling, why they can be useful for extraction of some particular information of this. Yes, Mark, you are right that now we are working, okay, for modern language models, we have like working at, not at word level, but like kind of part of the word levels. Yes, but okay, we have not very interpretable, but very powerful models. I think it's also the case for computer vision, and we also actually know nothing, but somehow it works and we are happy about it. So we kind of apply engineering approaches here, and maybe it is the way it should be, because I think that we need very complex model to imitate the words. If you look at human brain, they like orders of magnitude more neurons than like these models we have now, even like very large like BERT or GPT-3. But okay, it's kind of, we don't understand anything about human brain, and the same, we don't understand much about neural networks because they have too large number of parameters. Okay, but let's try to at least write some formulas and try to understand even some math. Not very hard in this case, actually, like any math in deep learning, I suppose, especially if you are not going to attend the course by Dmitry Yarovsky on statistical deep learning. So let's try. It wouldn't be hard, I hope. So to sum up, we have these word vectors, so we can use this table of embeddings, and for each word we have this particular embedding word vector here, and we can say the sentence is kind of these words like with each word at his or her own place. And we can say that sometimes when in this convolution or we in this subsequences of words, and we have concatenation of embeddings for words I to word I plus ash. And in this case, we apply convolutional filter. It's often easier to think that we have this guy as a long vector of size ash times k, where ash is the window size, how many words do we have here, and k is the embedding size. So we kind of multiply each component of each word by the related weight, and we then apply these convolutional filters. To get better results, maybe we can use filters of different size, so not only 3, what we looked at previous slide, but also 4, 5, and so on. In this case, I suppose we don't care too much about like being so by selection of odd size filters, we can do even size 2. And so if we apply all these filters to all our data, we have then features. Each feature corresponds to a part of this sentence. So we have C0 based on this part, C1 based on this part, and so on. We have some activation function here, maybe some linearity. this linear part, scalar product with the embedding, and maybe some bias. And so, after application of the convolutional layer, we have the embedding of size n minus h, where h is the filter size. We can do padding and do it to have it like r n. Okay. Nothing new, but now we have formulas. And what the paper did, they tried to use max pooling as the maximum value of this vector in these features. Also, the paper applied multiple filters with different weights and different window size. And also, okay, I repeat it one more time. When we are talking about this pooling, we are just dropping the requirement for processing of the sequences of different lengths. And we can say that no longer length is relevant. Instead, we apply the same technique for the sequence of all lengths, and we are happy about this. And to make a final decision, we apply another like logistic regression, or if you say it in terms of deep neural networks, it's a softmax layer with linear layer before it. So we concatenate all these filters in a feature map Z and multiply that by matrix W, add some bias, apply softmax, and voila, we have this specified result. So I suppose nothing too complex, but okay. But as we saw from this table, actually, this table was also from this paper. This kind of powerful approach that can be better than recurrent neural networks. Also, okay, often another idea that can be of some usage here is that often we can try to get embeddings from different sources. And if you have very large corpus, it's kind of good to have embeddings from this corpus. And so we can, for example, initialize embeddings within these vectors. But also we can do it like in two parts. The first part, we don't freeze, we train, we update it. And so we have like embeddings related to the particular problem. Also, we freeze another part. This is the same embeddings, like the second instance of the embeddings we had before, but we don't change them. So we have these two channels. We add them like before max pooling layer, and we kind of can improve with this not very sophisticated heuristics our results. And so finally, we have this whole one-dimensional convolutional neural networks. This picture is very similar to what we have like in this paper. Before, like that introduced CNNs for sequential data to the wide public. So let's look at it one more time. So we will have like 146% understanding of what's going on here. We say that we have three sides of the regions, 2, 3, and 4. And for each region size, we apply 2 filters, and we get 5 channels for it. And we apply for this input sequence, this embedding dimension 5 and 6 tokens. We get this 6 output of the first layer. Then for each feature, we apply max pooling. As we have 5 features, I suppose, okay, it's kind of mistake here, something like this. But maybe I am not getting something in this paper. But okay, let's do it my way and say that we apply max pooling along each dimension. So we have 5 features at each point. And we have like many features, at least at this step. So we try to, for example, apply max pooling for each vector 2. And so we have for 6 filters, 6 numbers. Let's concatenate them. Let's do it. And apply softmax layer in the end. And so we have for two classes probabilities for a sequence to belong to the first class and to the second class. And so it's it. Very simple model, nothing new, even simpler than convolutional neural networks. And it works quite good. One moment. To add, to finally specify the training and inference process. To make it work better, let's apply another trick or a bunch of tricks to improve the regularization. The first one is dropout. We say that this layer, this final layer, with softmax, we are not interested in some features sometimes, and we drop them with probability p, and in the end we learn a representation that generalizes better, and this is due to this dropout heuristic, which I suppose all of you also know. The second one used in this paper is not that common. Actually, I don't know if it was necessary or they tried it for one experiment, it worked, and they keep it to the end during the work on the paper. We calculate for each part of this sequence for the parameters a row norm for each kernel, or for each kernel and for this final softmax layer, and this alpha norm should be smaller than some constant s. And if it's bigger, we just divide it by like this norm. So we scale it, multiplied by s, and now it's equal to s here. And so kind of rescaling of weights. Maybe similar to batch normalization, but more on not on all gradient. Yeah, I suppose closer to gradient clipping, but we are not paying attention to gradient. We pay attention to the parameters itself. And again, I repeat, I am not sure if it was quite good idea, but in this paper they have this additional regularization. And so when we combine all parameters to completely specify the model, we see that it is something like this. Numbers that I suppose are typical. Maybe batch size is not very high. Maybe because the sequences are typically quite lengthy. And we have this word-to-vec combinations, these particular realizations. For stopping criterion, we just observe validation set error and stop at the point when this error starts to increase and we observe some overfitting here. So also not something that I suppose you didn't hear before. And in the end, we have this table. And as you can see, often these CNNs are very good guys. And you can see four different CNNs here that with different initializations. This guy is with random initialization. This guy with this non-trainable word-to-vec embeddings. This guy is with trainable word-to-vec embeddings, and this guy with both of them. So we have part of embedding that is not trainable and another part that is trainable. We train all those things. I suppose we can say what's the best option. I suppose maybe this guy or this guy. And definitely in general, they are very close to state of the art in all areas. And so if you compare them to RNN, for example, RNNs are much lower to train actually. It's maybe 2-3 times as per lower. For also this model is very simple. So as you saw as a figure, like a couple of slides before, you can really imagine that we don't put many efforts in selecting the architecture for this CNN. We just use the simplest model we can, maybe with some tweaks inspired by CNNs. So we can in general say that this is kind of state-of-the-art models, and it's still state-of-the-art model in 2020. Maybe not very as famous as transformers, but in many problems it can be useful and can even outperform the transformer, especially if we imagine something that that the range of dependencies is not very large, and we have to have convolutions that depend only on the part of the sequence that would be, and it would be the best model we have. 2 words to add to the slide is that, as usually, we should not completely trust these results, and we can think about some problems with evaluation from the very beginning. Maybe the most serious criticism is that we applied dropout is on these guys, because it was like a very recent invention. I suppose it was like in 2014 or very close to this. And most of the models before did not use dropout. So kind of, as we observe from this CNNs, that it has like plus 2 to 4% of accuracy. Maybe this benefit not due to the architecture used, but due to usage of this novel technique for 2014 dropout. So, okay, when you're doing your own experiments, try not to repeat this mistake. Or maybe, okay, you can use it to improve your results when you compare to others and state of the art. And the last slide, I suppose for today's last meaningful slide, is that we can try to do multi-layer deep CNNs for processing of the data. And here we see that this very deep convolutional metrics for text classification, 2016 paper. One of the authors, I think you know this guy, Jan LeCun. And again, we can improve over the result of what we had before. And we see that we are closer to what we are now often see for convolutional neural networks for image recognition. More layers, full connected layer in the end, instead of simple softmax. And we can improve at the cost of larger training times. Also note that in this paper they worked not at a level of words as tokens, but at a character level to make results look better. So let's see what we have learned from today. I hope it's not news to you, but CNNs are also a powerful tool for sequential data processing, and it's also a good baseline. Also, by this simple trick of max pooling and min pooling, we no longer worry about it. This pooling, or we have to proceed somehow this foreign length of sequence. We can do it with pooling. We can propagate the gradients, learn the network. We don't have this problem of the last token as the main token, as we have for CNN, or for RNN, we look at the whole sequence. So we can observe that these guys are good even if for very simple models. I suppose that if you try to do like one layer a CNN for image classification, you will not be too impressed, but in this case it works. And also if you have some trick from computer vision, then we can try to steal it and make it work on NLP data, on some improvement of this CNN architecture. Because many of the tricks works well, not only for processing of images, but also for processing of sequences. Now, okay, in this lecture, I described dropout, max pooling, multiple channels, and so on. And everything of it kind of worked here. Okay, and dropout also. And also one of the main tricks of CNNs, just use small layers. It works as well. And if you are tired of trying to invent new trick, to make more sense to your data, you can instead try to increase your accuracy by just using more layers of convolutional neural networks for sequential data. And I suppose it's all for today for the lecture. And as usual, I was happy to hear from you and happy that I hope, learned something new during this lecture. And also, I am happy to transfer the microphone to Rodrigo. Oh, it's here. So,
yes, I'm here.
Okay, very good. So, have a nice evening and goodbye.
So everyone, we'll have now a small break of 15 minutes. So 5:15, we'll meet again to have our seminar on transformers, on the attention mechanism. So let's meet again in 15 minutes. 1-5.